All right. All right. There's a few things about my analysis that I don't like, but we're gonna go for it for now. I'm gonna change it later, but this is my first analysis. So here you go. So analysis on the paper, this is complex network analysis of high frequency combustion stability in a model single element rocket engine combustor. This is a paper that's written by these people over here. And I'm just gonna learn something. There's an audio version of it that I made just because I know some people don't like to read. So I just made an audio version. Anyways, the idea is there's a problem, high frequency combustion stability in a rocket combustion is the problem. The idea is that there will be damages and vibrational heat problems and all that stuff. So we're going to use acoustic energy flux network to prove why instability happens with detach and attach of the rim injector. Attach at the rim injector small communities. You'll see what communities later. And basically, I mean, detach will be more unstable, but instability shear happens. And you'll see what that is later. Previous studies have shown the heat release coupling, injector effects, and flame detection, but the attach and detach has not been analyzed. There's three main points of this paper, which is Rayleigh-Taylor ratio, network, and the PZ mapping with clustering. Now we'll start with the in Vis's equation of a continuity, momentum, and energy. And first of all, we're gonna have to perturb everything. So perturbation, and then we finally get equation one after many perturbations. So equation one is the first thing we'll talk about, and then not the last thing, but the first thing. Anyway, with that said, we move on to this section over here where we similarly get few equations. So if we get first equation of pressure related to the Pacific heat, which is necessary, and then molar equation that really is necessary for later on. But you get these two equations, and basically you perturb it again. But before you perturb it, you need a basic state for this equation. So we get a basic state by getting rid of all perturbation, which gets rid of the dt and so on, which gives you this final form over here. A lot of math involved, but that's what you get. And later on, you combine equation two that we finally get after combining both of area because there's a what basically happened is that there's a heat term over here and there's a molar term over here, but you see how there's is one form over here to that. So we combine both of them instead of keeping all of them. So we're going to combining both of them to this one big equation over here, which then we're going to simplify by doing many by noticing the basic state, and then we get this form over here, which is going to be called equation two. This equation two then is combined by equation one. And then basically gets this final equation, which is a long equation, but you can look at this as the energy, and this is like the flux. And with that said, there's this term over here, which is the source, which is the most important because without that source, if this was zero, let me just imagine yourself if this was zero, there wouldn't be any instability here. There wouldn't be any way for this to be perturbed in a way that would create something because this will always go down to zero in the end of the day. So this is kind of like the energy term EA. And this is kind of like a little bit of a geometric term with the fluids. So you can kind of see why these two, if this was zero, would just go to zero naturally. And so there's a global averaging mode over here that if this is greater than, then this is zero. Oh, then it's unstable. And you'll see later on why that machine learning might have been an overkill for this thing, because I feel like there's a better way to do this, but we'll move on for now. For here, there's a Rayleigh-Taylor heat indexing over here, which is this equation over here. As you can see, it's an averaging again. This is actually a form of averaging. This is a form of averaging. And we have a production term here and so on and so forth. And you see over here, there's a ratio over here. And this ratio is interesting because what they found out in the paper is basically if you take this and get this form over here, basically the value that you get approximately is zero point 0.9 averagely. So basically, what happens is if you look at the heat release rate index and refers to the motor production, you see that this over here is about 10% negative direction. So what that means, the dampening of the molar indexing is about 10%. So now we know that basically this term over here is basically a dampener. Now, this is important because now I'm going to tell you a little bit later on that you really don't need to consider this a lot if you're thinking of instabilities. But that's for later. I'll explain why I think you can probably not have done machine learning and still got away with it. I think learning for this thing is overkill. But over here, there's a source term over here with delta y and delta z, and you see this y minus I and the pattern over here, and you see this strength network that you can use in to make an amp-efficient network and an anti-emitter, but it's basically just doing negative and minus plus, and then plus and minus over here, and then combining with the structure over here S, which is strength value. And this is like how you set up machine learning basically. And we're gonna slowly go over here. Now this is the reason why well, it doesn't matter for now, but this over here is a pressure term with the strength term. And as you can see, by looking at this over here, there's a jump, jump, jump. Every time there's a big jump, there's a big plus over here, excuse me, plus over here. So what that means is every time there's like a uh, Q that was strong, you're getting an instability basically. Um, and then this basically say amplification network is greater than anterior network and so on and so forth. Over here is how we model a little bit of the clustering a little bit, which is basically with Q. Q is if it's increasing the community is better, and you'll see what a community is. You see a P, which is kind of like probability. It spreads out, merges from 0 to 1. And ZI is how strong a node is, which is interesting later on. And I is just some kind of it's the community actually. But over here we can see that if there's a large scale hub forms and this means a large acoustic energy source appears and help drive the instability. It's kind of really hard to see with this like visualization, especially since the scales are way different. The scales are like this goes like over here really 10 to 3, which makes everything more confusing, but you can see the scales are a little bit off. But this is a clustering thing, which is kind of how we do a P to Z mapping. It's the first one that shows KSET. And you can see when there's near the inlet, we have a lot of clustering. This is a community actually, and we can see a lot of communities below the 5 range over here, and then a few in the 20 range. But the 20 range, you see, the Z strength is not really up there either, so it is not showing up as very strong right now. But as you can see over here, we see a more strength plus more communities in the red and orange zone, and you can see a little bit more over here. You can see the pattern over here. You're getting a more shear layer kind of section over here. And over here, you see some kind of pattern. And I believe this is the only part that neural networking actually was useful because it did tell you that I believe this thing induced some kind of source energy term or something. But other than that, I can clarify to you something interesting. The author I misspelled that, but use network method as a strong diagnostic, but the paper uh, could have done more to prove that machine learning was necessary, instead of only showing that memory was useful. So the neural worker gives strong evidence for this observation, but could have gone in medical old school with humans. Because think about it, well, you have this, right? You have this scale over here. Why not just plug it into here, take an integral, and we already know this is a damping term, right? So it won't really matter too much, but we can put that damping term in there too, just in case. And then we could just do a PQ analysis over here. And oh, guess what? They're always positive over here. Look, positive, positive. So what that means is basically this is never going to go negative. Therefore, it's always bound to be unstable here. And you can see by the periodic table over here, I'm pretty sure this is when basically You can see when it's dejected or something, and see that, oh wait, yeah, the most instability comes in and when it's injected or something like that. So I don't really like this question too much, but yeah.